Now that we've considered some natural transmutations or natural radioactive decay involving alpha, beta, and gamma particles, let's look at some more extreme examples of changes in the nucleus, and let's consider fission and fusion. So at their base, fission and fusion can be described in these two pictures that you should have in your brain when you consider the two of them. Fission is when we take a larger atom and divide it into two or more smaller ones. So it's a process through which a large nuclei breaks apart into two or more parts. Fusion looks somewhat opposite. It's when we take two lighter atoms, combine them, and then they move off as one single atom. So we have two lighter atoms forming a larger one. So at a glance, they look kind of like opposite reactions, but I'm going to convince you that they're not that different from each other. So here's an example of a fission reaction. If we watch, there was a neutron that hit this nucleus, and then it breaks into a couple of fission fragments, as well as a few more neutrons. So again, we'll watch this play through. We have a nucleus. It takes a little bit of jostling, but when we do that, it breaks into two smaller nuclei, and a consequence of that is also to release three more neutrons. So let's just make sure we understand generically what fission is. It's a reaction in which a large, unstable nucleus, that's this guy right here at the beginning, breaks into smaller nuclei, the ones at the end. And key to this is, in this process, the mass of the products is less. So whatever the mass of this large nucleus is, if we compare it to all the products at the end, including those neutrons and everything, add them all up, we are missing some mass. Einstein would say that's not a problem because in this reaction, you must be releasing energy in some form. And in this reaction in particular, it will be the kinetic energy mainly of those neutrons that move off at very high speeds. So we have this mass converting to energy that occurs in a fission reaction. And we can also consider that the nuclei that are being produced in this, the smaller nuclei, are more stable than the originals. Now, in a fusion reaction, smaller unstable nuclei collide, forming a larger nuclei, as you can see in the animation here. So we have a form of two forms of hydrogen, I guess, tritium and deuterium. They slam together, and as a result, we produce a larger nucleus, that helium nucleus that moves off. And again, there is this little byproduct, this neutron that also moves off in some other direction. Now, the result of any fusion reaction is that the mass of the product is less. So again, if we consider the mass of the tritium and deuterium at the beginning, when we are done, we add up the mass of the helium atom as well as the neutron, we find that we have less mass than we started with. That's not a problem. We know where this is going. Where's the missing mass? Well, it's converted to energy, and it's the kinetic energy, again, of the particles as they move off. So we're going to release a bunch of kinetic energy. The other thing to note, products in this reaction will be more stable than they were at the beginning. Now, you may have noticed that although they seem opposite in terms of, if you pay attention to the nucleus, one goes from a larger nucleus to smaller, the other goes from smaller to larger, the end result is still the same, and that is this. Each reaction results in a more stable nuclei than we started with, and we convert some of the mass to energy. So each of the reactions ends up with more stable nuclei and the release of energy. Now, how can it be that opposite-looking reactions, how can you get smaller nuclei that release energy and then produce larger nuclei that release energy? It all comes down to the chart that we looked at a couple of lessons ago about nuclear stability. So let's revisit that chart. And if you'll recall, it kind of took this general trend. Again, I'll remind you, this is the binding energy per nucleon. This is basically how stable the nucleus is. And as you move up this chart, you end up with more stable nuclei as you go higher, because you have more binding energy per nucleon. Down towards the bottom, you'll have less stable nuclei. And so you'll see this general trend that not a linear relationship. It kind of does this thing where it peaks out here and then it drops down here. So this chart that shows the relative stability of different isotopes is really the key to understand why we can have fission and fusion both result in the same thing. Consider large nuclei over here like lead, gold, thorium, uranium. In order for those nuclei to become more stable, they need to become smaller. They need to move this way on our chart. So uranium needs to become more like iron if it wants to become more stable. And for that reason, these large nuclei over here will undergo fission reactions where they go from large nuclei to smaller to become more stable to release energy that came from some of their mass. If we go to this side of the chart, we go over this peak here, this asymptote, if you like, and we consider what's happening to these smaller nuclei. As these nuclei want to become more stable, as in order for them to become more stable, they need to move this way on the chart. So they have this ability to become more stable if they become larger. So instead of being deuterium, this isotope of hydrogen, these are all, by the way, isotopes of hydrogen. This is hydrogen 1, this is hydrogen 2, this is hydrogen 3. Not that they're totally unstable, but they would become more stable by becoming larger. And so on this side of the chart, we see our fusion reactions occurring. So these small nuclei, lithium, beryllium, these things could become more stable if they could move in this direction, become larger nuclei. So from a physical viewpoint, fusion and fission are opposite because one is nuclei getting smaller, one is nuclei getting larger. But that's where the differences end. We still end up becoming more stable in both reactions, and both reactions will release energy because in both reactions we have a mass defect or a mass that is converted into energy. So because of the shape of this graph, because of the way nature works with this ideal most stable state being somewhere in here in the area of iron, that's why both fusion and fission can accomplish the same effects in terms of stability and releasing of energy by doing opposite things. Now, some examples of fission reactions. Well, fission reactions are the most common nuclear reactions that humans will cause to happen. These are the kinds of reactions that currently take place in nuclear power plants, where some sort of a fuel, such as uranium or plutonium, is used. It's purified, and then we allow that to undergo its kind of natural progression. So we will take a uranium, for example, nuclei. We will bombard it or shoot a neutron at it. That neutron causes this thing to break apart. And remember, the consequence of that was it released 3 more neutrons. Guess what happens to those 3 neutrons? Is they will run into yet another uranium nucleus, or maybe 2, or maybe even 3. And if you've heard the term and understand it, you can see why we get this chain reaction. Whoops, only one arrow there. This one hits here, this one hits here, this one hits here. You get the idea. So if each of these single events, each of these one fission reaction causes 2 or 3 more, then we get this exponential growth. And what little energy was released here becomes more and more and more energy very quickly. This is your typical nuclear power plant nuclear reaction. Left uncontrolled, this will become a bomb. By slowing down or blocking some of these neutrons, we can control how much power is generated at any given time. Fission reactions, well, sorry, fusion reactions, Those kind of reactions happen in stars. So in stars, we have the really good conditions for small nuclei. I'll keep it really simple. Let's imagine we have a proton neutron style of hydrogen and a proton neutron style hydrogen, so deuterium and tritium. In stars, two things are necessary. They're very dense, and more importantly, they're really hot. And what that means is these things can be moving extremely quickly, fast enough to overcome their repulsion that they will feel at a distance, and they will eventually fuse together. So in stars, the conditions are right, this dense, hot ball of gas, that fusion can occur, and the result of the fusion reaction is we create this proton, proton, neutron, neutron, helium atom, and a neutron might come off as a consequence with a bunch of energy, and that energy is the energy that is released in the form of radiation from the star, like our sun. Humans can create this kind of a reaction on Earth, but again, we have to kind of do the same thing stars do, which is create this really dense and hot mixture of gases so that this fusion can take place. The big challenge to fusion is how do you get these particles close enough together that they actually do fuse. The simple way to do it is using heat, just to get enough kinetic energy that these things have enough momentum to squeeze together. But humans are always looking for better ways to do this, because if it's not clear from this little diagram, the result of this thing, producing helium as part of your reactor, part of your energy producing device, is way better than producing, well, let's see what we have here. We started with something like uranium, and we end up with some depleted uranium. So this uranium broke apart into some different parts. It becomes, I think, krypton and maybe beryllium or something like that. I can't quite remember. But those in themselves aren't that dangerous. But you still have a bunch of uranium, and the more this reaction takes place, the less uranium there are to hit. So at some point, this becomes still highly radioactive material, mostly uranium, but not enough to really power your generating plant. So you end up throwing out a lot of uranium fuel cells that still are highly radioactive. So fusion would be a much preferable way of producing energy here on Earth, and we're just not quite there yet. So that's the concepts of fission and fusion reactions. I would advise think about them in terms of physically what they look like, understand that so you understand which one is which, but then recognize that both end up creating more stable, less massive nuclei, and in that process release energy. The only math that you have to worry about is good old-fashioned E equals mc squared. Once we know how much mass we lose or how much mass is converted, we can figure out how much energy is released.